Hello, my name is Ivan Taylor, and I'd like to share with you today a review of the highly accessible and important book, uh, How Big Things Get Done, by Bint Flyvbjerg and Dan Gardner, and mainly focusing on resilient systems. Flyvbjerg has collected over 1,600 mega projects in a database that covers 136 countries and 20 fields. He classifies projects into two categories, common and one big thing. For common projects, reference class forecasting, where you look at how long similar projects took and how much they cost, can be exceptionally useful to accurately estimate your schedule and budget. Some of these projects may have experienced black swans and unknown unknowns, which may not be the same as you will experience, but may have a similar impact. For projects that Flyvbjerg calls one big thing, reference class forecasting may not be possible because of the small sample size. Adversities can kill these projects, whether they are black swans or multiple small adversities that combine into a perfect storm. And as we will see shortly, Flyvbjerg suggests many common sense heuristics that can be used to make these types of projects successful. Data analysis reveals that on average, mega projects experience a 62% budget overrun, but the distribution is fat-tailed, so the situation is much worse than this would suggest. 91.5% of projects are over budget or late. 99.5% are over budget, late, or falling short of expected benefits. It is estimated that mega projects will cost as much as $22 trillion annually over the next decade. And even a 5% savings on these projects would represent $1.1 trillion, surpassing the GDP of South Korea. This highlights the importance of high-quality project management and project execution. Flyvbjerg presents a set of heuristics that project leaders can employ, which include: hire a master builder, get the team right, ask why, build with Lego, think slow, act fast, take the outside view, watch your downside, say no and walk away, make friends and keep them friendly, build climate mitigation into your project, and know that your greatest risk is you. While discussing successes is essential to highlight the resilience exhibited by these projects, by applying these heuristics, these projects demonstrated their ability to navigate challenges, adapt to changing circumstances, and achieve successful outcomes. The Empire State Building project successfully employed several heuristics, hiring a master builder in renowned architect William F. Lamb, and assembling the right team by choosing a construction firm famous for putting up skyscrapers. They acted fast, building a 102-story building in less than 14 months. And they made it with Lego, not a 102-story building, but 102 one-story buildings, learning one floor at a time. Terminal 5 Heathrow focused on three critical heuristics. Firstly, they planned slowly by using highly detailed digital representations to run rigorous simulations. They built with Lego by sending materials to factories that used detailed digital specifications to manufacture components sent to the worksite for assembly. They made friends and kept them friendly, getting the contractors to work together. The Guggenheim Museum Bilbao employed several heuristics. They hired a master builder, 62-year-old Frank Gehry, who asked why. Why were they building the museum? They wanted to draw visitors and invigorate the economy. Why renovate an old warehouse? Why not build a dazzling museum on the waterfront? He planned slowly, using models of wood and paper, often multiple models a day, and eventually building models on an especially modified version of the digital simulation software CATIA. Wind and solar farm projects implement the heuristic of build with Lego. The basic building block is a solar cell. Multiple solar cells form a panel. Ship and install the panels, wire them together, and you have an array. Add arrays and to generate as much electricity as you like. Modern windmills consists of 4 elements: a base, a tower, a head, and a blade. Snap them together and you have a windmill. Add more windmills and you have a wind farm. Tesla Gigafactory 1 embraced the heuristic of build with Lego. It's the world's largest factory by footprint. The Lego was a small factory. Build one, get it working, build another beside it, and integrate the two, build a third, a fourth, and so on. The British High-Speed 2 project prioritized the heuristic of watch your downside. Opportunity is less critical than risk. Risk can kill your project, and no upside can compensate for that. High-speed rail is fat-tailed not because of catastrophic risks, but dozens of standard risks that compound into a perfect storm. A common problem of digging in England is archaeology. There is a good chance of uncovering ancient relics. Then work must stop while qualified archaeologists survey the site, document it, and remove the artifacts. Artifacts could be found on multiple sites, leading to a chain reaction of setbacks. The solution HS2 decided on was to put every qualified archaeologist on a retainer. The Nepal School Project integrated the heuristic in built-in climate mitigation. They built 20,000 schools in the Himalayan country of Nepal, in the poorest and most remote regions. Recognizing the region's vulnerability to earthquakes, the schools were designed to be earthquake-proof. The schools stood in 2015 when a massive earthquake killed 9,000 people. They also built with Lego, focusing on the classrooms and combining 2 or 3 classrooms to make a school. The classrooms had only 3 designs based on the slope of the construction site. Conversely, the following failures we examine provide valuable lessons as well. By understanding the heuristics that were not effectively utilized, we can learn their importance in project management and decision-making processes. The California High-Speed Rail project failed to utilize a master builder. When announced, foreign companies with lots of experience set up offices in California. However, the state decided to hire many inexperienced US companies overseen by managers without experience in high-speed rail. The Great Belt Bridge and Tunnel project in Denmark encountered difficulties due to the absence of a master builder. It was led by a Danish contractor with little experience in boring tunnels. There were delays in delivering the boring machines that needed fixing and redesign. Then 2 tunnels flooded, damaging the boring machines. They had to pull out the boring machines, drain and repair the tunnel. The Canadian Icebreakers project failed to utilize a master builder. They planned to build two icebreakers, but instead of using one experienced European firm, they contracted to two Canadian companies, one in Quebec and one in BC, so they couldn't even learn from building one icebreaker after another. The Montreal Olympics project in 1976 faced significant challenges because it failed to utilize a master builder. The Olympics aggressively marginalizes experience by moving the games from region to region every 4 years. Flyvbjerg calls this eternal beginner syndrome. They also want to be unique, such as the biggest, tallest, most unusual, most beautiful, and most unique. The Montreal Olympics was 720% over budget. The Sydney Opera House project encountered difficulties due to a failure to utilize a master builder. Jorn Utzon was a 38-year-old who won the competition with nothing but a magnificent doodle. They didn't think slowly. Joe Cahill, Premier of South Wales, who was dying of cancer, wanted to leave a legacy. Construction started in February 1959 before the March election, and Cahill wanted to make such progress that no one who succeeded him could stop the project. Rushed construction had to be dynamited and cleared away to start again. The Montjou nuclear plant project suffered from a failure to act fast. The longer the window opens, the more likely a black swan will fly through. Construction started in 1986 and finished in 1995, but a fire shut down the facility and a cover-up kept the plant closed for years. The project restarted in 2005 and had test runs in 2010 with the planned operations to start in 2013. A black swan of Fukushima in 2011 turned popular opinion against nuclear energy, and in 2016, Montjou was permanently closed without ever producing any electricity. The XRL mass transit project from Hong Kong to mainland China encountered challenges due to a failure to take the outside view. The company had lots of experience with big transportation infrastructure, but no experience with high-speed rail, which is exceptionally complex even without being cross-border and underground. The Apple PowerMac G4 Cube computer failed to ask why. It was released in 2000 and was a translucent cube that looked gorgeously futuristic. It had no power switch, you just waved your hand. It was molded by Steve Jobs' passion, not by looking at Apple's customers' desires. G4 flopped and was scrapped a year later. The Amazon Fire Phone also failed to ask why. Amazon begins with a press release summarizing why it is valuable for customers and a frequently asked questions documenting costs and functionality, then works backwards from there. These documents are reviewed in a 1-hour meeting with no PowerPoint allowed. These documents are read in silence, then people share their thoughts with senior people last. Jeff Bezos devised the 3D Fire Phone. It was released in 2014 but didn't sell. They dropped the price by half, then made it free. They couldn't give it away. It was discontinued a year later and hundreds of millions of dollars were written off. Asking why can only work where people feel free to speak their minds and the decision makers listen. No one was brave enough to take a stand and win an argument with Bezos. Theranos needed to see that their biggest risk was themselves. They raised $1.3 billion and had George Shultz and Henry Kissinger on the board of directors. They claimed to have developed a spectacular new blood testing technology, but it was a mirage and led to fraud charges. Here are the key takeaways for INCOSE systems engineers to build resilience into big projects. Involve expert systems engineering professionals who would be considered master builders. adopt model-based systems engineering, which would be the equivalent of thinking slowly to make a foolproof plan. Incorporate loss-driven systems engineering to identify and address risks, which would watch your downside. Utilize reference class forecasting to estimate budgets and schedules, which will include the impact of black swans and unknown unknowns. Use proven technology, which Flyvbjerg calls frozen experience. Implement modularity in your design so that when it comes to execution, you can act fast and get results quickly. This book includes many contradictions. For example, not all successes followed all of the heuristics, and some failures followed many. However, I would recommend this book, and I think it highlights many of the initiatives in INCOSE and could help INCOSE members explain the value of systems engineering to stakeholders in a highly accessible way. Thank you for your time, and if you have any questions, we can take them now.
I think it's a great presentation. You have a good overview of the book in general. One thing that I could have asked question is, you mentioned black swans, and at the end you said unknowns. What do or how can you see them, or can you prevent that?
I think that you can't really prevent unknown unknowns. I think the idea that Flyvbjerg has is that almost all projects will face unknown unknowns, but they may all be different unknown unknowns. And if you look at many projects in the past and see how they handled things and how much they cost to build and how long they took to build, you can use those numbers to estimate your own project. And because those projects had suffered unknown unknowns, you would build in the penalties and the costs of unknown unknowns happening to your project.
Thanks. Okay. Yeah, I think that would be my only question for now.
Okay.
One thing that I can reflect from your presentation is, for example, the construction of the Barcelona's cathedral, the Holy Family. It's been in construction for more than 100 years, and one of the well, it faced a lot of uncertainty because the architect died in the first years of construction, and he didn't wrote a plan or a set of blueprints for the whole project, right? And since then it has passed the project for the next architect, right? So it might perhaps what it's built right now doesn't reflect the vision of the first architect that started everything, right? And it,
Yeah.
but you didn't have, or he didn't have modeling, right? Or CATIA, or
Yeah, that's true. But even looking back at the Empire State Building, it was built in late 1920s, early 1930s, which is almost 100 years ago.
yeah.
But it was built in only 14 months, and it was quite an architectural achievement. And I think that yes, it's a real failure to start building without a good plan.
Mhm.
And that was one of the problems that was faced by the Sydney Opera House, that they started building without having a proper blueprint, as was described by Flyvbjerg. All they had was a, a, a fancy doodle of a design with no real idea of how they were going to put together such a complex building with these great wings and amazing types of architecture that basically had never been built before. And so they didn't build a proper plan. They didn't have it all worked out before they started. And again, this was basically caused by the politics of the situation, where the
Mhm.
premier of South Wales was looking to push the project to build his legacy, and he wanted to get it started right away without any waiting to build to to build a proper plan. And Flyvbjerg has some very interesting ideas about the problems of politics and psychology as two of the major problems involved in big projects.
Mhm.
Politics, like I said, with the Premier of South Wales and many of the people who promote big projects for political ends, and also psychology, where people are suffer from optimism bias and sunk cost fallacy, and they suffer from things that have been well studied by psychologists as particular problems in decision making. And the combination of psychology biases and political motivations can lead to terrible disasters in the production of big projects. And Flyvbjerg, I think, has a very good point that we really can't afford today to have these great wastes of
Mhm.
money on these projects. There's too many important things to do with, for example, climate change, that we can't be wasting money on a lot of these projects. We have to do better. And so he's hoping that through his very accessible book, that he can get some of these ideas across that will really make these projects more likely to meet their objectives. Uh, yeah, so it's very interesting. In the book, he talks about all the things that need to be done if we're going to be able to fight climate change,
Mhm.
and get to a proper a level of emissions by 2050. And the costs are enormous, and it'll involve a great deal of cooperation, and we really can't afford to make mistakes the way we've done in the past.
Right. Perhaps that's where model-based decision making comes into place, right? If you can remove uncertainty by exploring the underlying model or the underlying structure of the problem.
Yeah, I think that, like, basically, like I said, we can't afford to have these major mistakes, and so modeling the system before you build it. If you do a good job, hopefully you will be able to see where to put your effort to avoid the problems that could
Right.
happen, and how to make the project, like I said, foolproof, and get it done quickly and effectively. So his idea of thinking slow by using model-based systems engineering, and then acting fast by using modular design, and always thinking about how you can modularize things, I think it's really a powerful ideas.
Right, right. That's the concept of using Lego, right?
Yeah, using
Like
Lego. Yeah.
building blocks to create your whole structure.
Yeah, and in his book, he has a number of examples that you wouldn't necessarily think would be actually able to use Lego. But there are amazing innovative ways to do it. Like for example, instead of building one giant hydroelectric plant, you could have many smaller plants that actually, you can actually build them quicker, smaller ones quicker, and actually
Mhm.
produce electricity before the whole project is over, and not having to wait till this great giant hydroelectric dam is finished before you're
Right.
producing electricity. And similarly, he talks about how the nuclear energy program is starting to look at smaller reactors, so that instead of building a giant nuclear facility, they build a number of smaller facilities, and thereby build them quicker, and produce more energy as they're building.
Right. Right.
So
Yeah. Well, for I can relate to what Tesla did in the test in the Gigafactory one, because right now they're building the new Gigafactory here in my city, and they say that if the first one, if the last one was made in 14 months, then they will try to build it in less than that time. So
yeah.
I guess it's gonna be a great project.
Yeah, basically, the idea to, again, like for example, with the Canadian Icebreaker project, is, that project failed to learn from the experience of the first icebreaker.
Right,
Whereas
right,
Tesla, in building a small factory and then building a second small factory, they have this great learning curve. And if the factory
right.
is very similarly designed, then they learn how to build it better. And similarly with the Empire State Building, the floors were so similar that basically they got to be very efficient at building those floors by the time they got to the end. They were building, I think, something like 14 floors a week at one point.
Wow.
Yeah, so it was it took a long time for the first few floors, but
Yeah.
as they got higher and higher up, they got better and better at building those floors.
And in a way, you have a compound effect, or you have a feedback loop that helps you create more knowledge as you go
Yeah.
building.
Yeah, I think that's true. Actually, the common language of that is a learning curve, where basically you have some kind of an exponential effect on reduction of time, or reduction of cost. That basically with every unit you make, you cost less per unit.
Right.
Okay, well, thank you for
Great.
your time, and I'll shut down this recording.